Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. Right here on Twitch with no engines and no libraries, it's just us and old school programming here. We have built ourselves quite a bit of stuff over the past 160 hours of programming, and we're kind of getting to the end of our engine development here, slowly winding down to the point where we will have done all the stuff that we wanted to do for support, and we'll sort of be moving a little bit into game programming. But we still have a couple big things to go. And right now, we kind of got to a point where we could, if we wanted to, call our asset system done. But I kind of wanted to talk about a couple other things related to it, just to sort of give some perspective on it. Right now, what we did yesterday is we finished transitioning our asset system over to something where it uses a relatively fixed amount of memory to operate. So it will free assets when it needs to load new ones. It'll go find ones that aren't used or haven't been used recently, free those and load in new ones. So we've done that, but the way that we did that is I showed how to do the structure of that, given that you could ask for and give memory back to the operating system. So the operating system's virtual page table was basically substituting in for a general purpose allocator for our purposes, which is actually probably fine in 64-bit, but I don't know that it would be fine in 32-bit. I'm not 100% confident about that. And unfortunately, we don't really have a lot of great ways to test that at the moment. Since we don't have the full game done, we don't really know. We can't just run it under 32-bit and see whether the asset load and usage patterns happen to create problems or not. So I don't really know. But what we might want to do, at the very least, is take a little bit of a look at writing our own general purpose allocator in there for educational purposes. And, we can write it in such a way that it's free for us to switch between the two, right? And that way we could get a little perspective on it, but still always have the ability to switch to the operating system's one if we find that that's more expedient or more useful. So I think that might be what we'll take a look at today. But before I do that, let me point out that today is day 160. If you have pre-ordered the game on handmadehero.org, then what you want to do is unzip day 159 source code into a directory. That is the source code that I am starting with today. And so you will be able to follow along at home if you start with day 159. All right, so where we left off, let's see here. Let's go ahead and load this up. Where we left off is we had everything kind of working and paging out assets, and it was just we were forcing it to use a very small asset size, a total asset footprint, and it seems to be doing that just fine. We can do whatever we want, and it seems to handle it, no real problems with that. And yes, we still have like heads spewing out of us. That's just something that happens now and again. There's no reason to be alarmed about that. It's all fine. But what I was saying was that if you take a look inside handmade asset.cpp, what you can see is that we were calling an allocate function. We have these two things, acquire asset memory and release asset memory. And what we were doing there is we were just basically punting to the operating system and asking the operating system for a new set of pages every time we wanted to store an asset, and then releasing pages back to the operating system every time we got rid of an asset. Right? So if we wanted to, what we would do here if we wanted to basically do the memory allocation entirely ourselves is we just want to replace these two functions, acquire asset memory and release asset memory. We want to replace those two functions with functions that we could implement ourselves that would allocate or free the memory, right? So that's what I mean by writing a general purpose allocator. You notice that these are completely general. The assets can be freed at any time or allocated at any time. There is no stack-like structure to it, which most of the things in a game are happy to use. And that is why we get away with not really needing any general purpose allocators or any other things like that anywhere else, right? Essentially, by structuring things so that they operate on stacks, what that basically gives us is it gets us out of having to deal with any lifetime issues. So that's why we don't need a garbage collector, right? Or anything like that. We don't need to, and we don't need smart pointers. We don't need any of that stuff, right? So it gets us out of that. And it gets us out of having to write something that does allocation placement because we know that things just come in order, right? So basically, structuring with stacks actually gives us this twofold benefit. It allows us to, not have to worry about lifetime stuff, so no garbage collectors, no smart pointers, that stuff, right? So that's great. Gets rid of all that complexity and any kind of performance problems. All that stuff is gone. And it gets us out of the notion of having to figure out where to place things in memory, which is kind of a separate thing from lifetime management. And that, of course, is because things just can come in order and get popped off in order, right? That's the nature of a stack. And so what we have in the asset system is we don't really have a lifetime management problem because all that stuff is very clearly known, and the asset system itself does its own least recently used tracking of that. So again, it's a kind of a virtual memory scheme in there. So we've done the work to figure out what kinds of lifetime stuff we want to have happen. And so we don't need any of the others. So we don't need smart pointers or garbage collectors or that sorts of things because we, once we actually write the algorithm that we actually want for figuring out lifetimes, which was that sort of circular linked list thing, those other things are extraneous. We don't need them. But we do have the problem of where to place the memory, right? And that is the part that we are left with here, right? So what you could imagine is if we were to take sort of a giant chunk of memory and say, all you get, Mr. Asset System, is that giant chunk of memory. What are you going to do when we do acquire and release asset memory? How are you going to manage that, right? How are you going to deal with what's going to happen as that stuff gets allocated and freed? And we talked about essentially the fundamental problem there, which is that you've kind of got this structure happening, and if you imagine what happens in our stack, you allocate asset A, then you allocate asset B, and then you allocate asset C, and then maybe D and E, and they're all different sizes, right, currently, and so on. And so what we want to do is we want to say, okay, at some point, we're going to have to allocate a new asset, right? And that's going to be asset H, but we're full up. There's no room for asset H in here, right? So now we have to figure out, we want to evict least recently used people, and maybe we start to evict least recently used people. We get into a situation where we can't fit it. So maybe B was the least recently used, right? Now if B was bigger than H, or the same size as H, we could just slot it right in there, right? But unfortunately for us, if it's not, then H can't fit. And so then we have to evict the next, we have to evict more things, right? Like maybe A or something, right? And then we would know, oh, okay, H can fit in here, and so then we're able to place H, right? And you can see that's a pretty hard problem. You could see that if you really needed to make this very tight and very good, you could sort of see this being actually a very big time investment on a project if you felt like this was crucial to the success of your game, for example, which it's not going to be in Handmade Hero, because we have probably plenty of memory to play with. But if you were like really obsessed with getting the smallest possible memory footprint and the most possible asset preservation, you can see how this would be pretty complicated, because in this case, like, you might look and say, oh, well, the least recently used was B. The next most recently used were like was like E and F, right? And E and F taken together will fit H, but B won't. And since freeing B doesn't help us put H in there, we just shouldn't free B, right? We should free these other guys instead, right? And that's a really complicated thing to think about, because you need to think about like where they are and like what will happen when you free multiple of them. What if it was like E was the least recently used, and then B, and then F? And so then you'd have to know to like free E, skip B, leave it there, free F, and then you'd figure out that it would be big enough, right? You can see this is really pretty complicated, right? So hopefully you can kind of appreciate that this is sort of a whole domain of interesting problems. Memory placement and fragmentation management, that sort of stuff, is like a whole field. And you could choose to spend months if this was your jam, or if it was very important for something you were doing, like optimizing this sort of stuff. And when I say optimizing, I don't mean like fiddling with SIMD, like to get like cycles down or whatever. I mean algorithmically thinking about it and changing how your algorithms worked and building interesting data structures and doing, who knows what. Now, I might also suggest that if that was what you were going to do, though, that maybe picking one of the other options that we had further up the chain, like making the asset files be broken into tiles so that you know you always load things of similar sizes and stuff like that, that may have been a smarter thing to do, right? And so you might make different decisions if you decided this was the thing that was most important to you as well, and that's sort of a separate issue. But again, if it turned out that you were in a situation where variable allocation was necessary and it was crucial, it's kind of this whole separate field that you could go into and look into. And we're not going to get that hardcore on it because there's really no need for us to do so, but I just wanted to kind of make you aware of that. So let's talk about this a little, like how would we go about implementing something like this as a very straightforward kind of a thing. So you can kind of imagine what we would have at the beginning is we just have a gigantic empty piece of memory, right? We'd just say like, oh, you know, we'd have, and to be fair, we might say that we don't have one gigantic piece because maybe Windows can't, on 32-bit Windows, you know, maybe we want to use 2 gigabytes. Well, that's not realistic. Maybe we want to use 1 gigabyte for our asset storage or something fairly large. And on 32-bit Windows, it can't find 1 gigabyte of contiguous memory or something like this. And so trying to virtual alloc 1 gigabyte as something to give our app might just not work. Okay? So what we may need to do is say, okay, we would start off with some series of things, some series of free regions, right? So it wouldn't necessarily be one big one. It would be something like a few regions that we get handed from the operating system, right? So we've kind of got a set here, right? And each one of these is something like, you know, maybe each one of these is 256 megs, right? I don't know. Or maybe it's like, you know, maybe that's too big. I don't know what it would be. It'd be whatever we could get away with, 64 megabytes. Who knows, right? So we'd have some number of these chunks, and we would need some kind of a free list, basically, some kind of a thing that manages the memory that we've got. Where we could sort of say, okay, when I need to allocate something, I'm going to take some space from one of these things that's free, right? And we could fill them up initially just like the stacks, so then we could put something, if we needed to put something in there, we put something in there, and now we know that it's got less free. So now it's got, you know, 59 megabytes free or something like that, right? Who knows? So there's something like that. And then what we need to be able to do eventually, and that's pretty easy, right? And when this gets full, we can just put it in the next one. So what we would need to do is basically have some kind of a list that sort of says, okay, here are the things that we've got free, right? Here are the places we could put stuff. And when we need to put stuff, we look to see if any of them can hold it. If they can, we put it there. If we don't, they don't, right? And so where things start to get more complicated is when this starts to get, you know, this could start to get a little bit trickier. But, you know, if you think about it, that initial situation where I just have a couple of these free, that's really all that the same thing is going to happen once I start getting fragmentation, right? If I have some guy in here who's got like a couple things, right, free, I mean, or a couple things filled, and then I free something out of the middle, right, and maybe free something out of the top, then really what I could think of this as being is just another set of fragments here, right? I could just think of us as having more fragments. Here's one free fragment, and here's another free fragment, right? So in some sense, you can sort of see that like we can start to think about the memory as sort of this concept of some series of blocks which could have stuff put in them, and each of them has like a size, right? So each of the allocator, each of the memory regions has some size, and it's like this much memory is free. And then in some sense, when we're actually doing the allocation, we don't really even have to think about the parts that are filled, in some sense, right? We just have to think about the parts that are free. Because the allocator just needs to know, is there a chunk of memory that could hold this thing that I'm trying to put in it, right? That's all it really needs to know. So where things start to get more interesting in terms of having to think about the actual filled space is when stuff gets freed, right? So if I take a view of this block here, right? If I were to just view this block, right, of stuff, where I've filled it here and I filled it here, but it's empty here and here. If I were to think of that as just disjoint regions, right? Here's region A, here's region B, and I've got A and I've got B, right? Well, that would work fine for allocation, Nothing wrong happens with allocation. We would just look at A and say, can we fit something in A? We look at B, can we fit something in B, and party on, right? But what happens when we free this block right here, right? It's between A and B. If this block got freed, then A and B are now actually not separated anymore. There's a contiguous thing there. So they can actually become a bigger single contiguous block for allocation purposes, right? They can become, A, B, C, this whole block, right? So even though when we're allocating we don't actually care about the filled space, we do need some way of knowing that there is free space. Of the filled space. We need some way of knowing that there's filled space, because the only way we can know to recombine memory back into bigger chunks is if we know when we free the free space where it lay in relation to the other chunks of memory, right? So that's how that works. That's what we're going to have to do. Now, what are some other things we know? Well, this is an asset system. So basically, there's no small assets, right? So basically what we're talking about here is we don't have to worry about things like someone allocating 1 byte or 16 bytes. Nobody's going to be allocating small things. People are going to be allocating things that are like 64K or something, right? They're going to be allocating chunks that are reasonably sized. And what that means is we're never going to have really any situation. We could pre-declare that we're never going to have any situation where the free space itself couldn't fit a fair bit of data in it, right? That can just happen, right? It's not an issue. And so what we could start to do here, just thinking about it, right, is we could start to think about saying, well, okay, if we just wanted to do this in a very inefficient fashion, you could imagine doing something where we have blocks of memory, right? And those blocks of memory are laid out such that every free block of memory, kind of on its either side, has some information about what comes after it, right? Or who it is even, something like this, right? So you can imagine that if we freed this block of memory and we wanted to know if we could merge it with the block above it, right? You could imagine us doing something where we actually have some information about that block stored right in, sort of in lines with the blocks themselves, right? You could imagine some kind of little like header information that's in there in such a way that we wouldn't have to use an out-of-band piece of storage for it, and so that we wouldn't have to we wouldn't have to really worry so much about how many there would be, because it's just a block of memory, and however many chunks you dice it up into, those chunks themselves would store little pieces of information in them that let us know what we would do with those chunks later, right? So I don't know, you can kind of see what I'm getting at here. There's probably some options we have for just putting in line with the memory the information we would need to do, say, the merging operation, right? That's plausible. So yeah, so there's stuff like that, and we can start playing with that. So the real thing, and if you think about that operation, it's not very complicated. I'm going to free this thing. I need to check to see whether I merge it up or merge it down, or both, right? That's a pretty easy thing to conceptualize. Like, it's not that hard to figure out how we're going to do it. That's like really not something to be too concerned about. What's a little bit more concerning, right, is the allocation side. So let's say we've got all these things. Let's say we did the simplest possible thing and just strung them together, right? So we've got, something that looks like this, right? And we've got some stuff that's actually being used in there, like so. Something like this. So let's say we need to allocate something. And what we have is some kind of threading, so we can kind of go like, okay, the first free block is here, and it points to the next free block, and that points to the next free block, and that points to the next free block, and that points to the next free block, right? So what we could do is when we need to allocate something, we just walk all the free blocks, right? We just walk them all the way through. And after walking all the way through, we just make a decision about what we want to do in terms of which one we want to put it in, right? And presumably, the one we would want to put it in is the free block whose size is like, closest to the size we were looking for, because that leaves the least fragment. Or another way to look at it would be if we were to put this piece of this asset into this block, what would the leftover block size be, and how well do we think that leftover block size will actually do we think that leftover block size will be usable for anything else, right? And one of the interesting things about our system is that when we load in our asset files, we actually could spin over them quickly once and determine what all the actual asset sizes are, right? That's something we can actually do. And so we would know, for example, a rough histogram. If we wanted to, we could imagine something where we could actually plot. We could say, here's a histogram of sizes, where we go like, here's the sizes. Okay, we've got 4K assets and 8K assets and 16K assets and 32K assets and blah blah blah, right? And we know we have some distribution of these things, right? Something like this. We are actually in a position to make a heuristic call somewhere, right? We're in a position to sort of say, if we wanted to, fairly accurately, what the chances are that we're going to hit an asset, that's in a certain size range, right? Because if we know that, there's 4,000 16K assets, right? But there's only, 200 or something. Not to scale. So, if we know that's the case, then we would not be super concerned about something that left, say, a 17K size, because we'd be like, well, we'll probably be able to fill that. But if the opposite were true, and we had almost no we had no assets less than 16K, but a ton of assets greater than 16K, we'd be pretty nervous about leaving a 17K fragment, because what are we going to put there? Very few things could go there. So, there's stuff we could do like that. So yeah, so that's the situation as it stands at the moment. And it's pretty complicated what we're dealing with here. It's like I said, this is pretty complicated code. It might be one of the most complicated things we do on Handmade Hero is this part of the asset system, right? The whole, and when taken together, the whole okay, background assets are being streamed in and they're being used in the ground chunks, and they have arbitrary memory sizes and all this sort of stuff, right? You can kind of see how there's a fair bit of complexity here compared to, say, the renderer, which, despite the fact that it's a very it's very mathy and it's very intricate, it just doesn't have the same level of sort of, I want to say, interlocking pieces. It's more like everything is a very well isolated thing. It's like, here's how we fill a pixel, and it just kind of happens right there, and it doesn't have all these sort of competing things going at the same time like the asset system does. So really, I think the asset system is probably one of the most complicated parts when you think about it that way. So anyway, yeah. So we've got about a half hour left. So let's just play around. Let's see where we get. We won't try to do anything particularly fancy here. But yeah, I mean, point being, you can kind of see why there's a fair bit of complexity here. And there's some things about our asset system. The fact that we have background threads using the asset system is also makes things more complicated, because it means that at the point where we allocate memory, we can't necessarily guarantee that we can free memory at that point, and other sorts of relatively complex things such as that, right? Is that actually true, though? That may not be true. That may not be true at all. To be honest with you, I think I may have been operating on a slightly false assumption. It may be that we actually have a lot more flexibility there than I was going to say. Because when an asset is being loaded, its state is set to queued, and we never free an asset whose state is set to queued. So actually, I guess we can just free assets just fine in the middle of that. So I don't really know why I said that. In fact, the evict asset stuff, I may just have been wrong. It may be that we can just flat out evict the assets like in the middle of that thing. Because move header to front never is allowed on locked assets. So assets that are in the background ground chunk stuff can't be happening. So it's only happening when assets get used. And assets get used only in the main thread. And so I feel like, yeah, I mean, I feel like almost we actually can evict assets right in the place where we actually need to do the load. So I may have been wrong about that. I feel like we could almost do it this way, now that I'm thinking it through a little bit more. Which is that we could make it so that up here, evict assets as necessary, right? We could make it so that we only do this step when we do acquire asset memory, right? So evict assets as necessary is not actually going to be something that has to be pumped. Am I missing anything? I don't think I am. I just don't think I am. I don't know. I could be wrong about that. We'd have to think it through very carefully, obviously, but I feel like that's a fairly safe statement to say. I feel like, we can just evict assets as necessary. We can just call that when we do an acquire. And when we go to do an acquire asset memory, that could be the time that we call evict assets. I'm going to try that. I'm just going to go ahead and do that here. And then I'm going to get rid of the call to evict assets as necessary that's in here, right? So evict assets as necessary is just going to go away. Maybe I just, because I thought before we would need to do that. And I'm just wondering now, I just don't know if I was wrong or not. I don't know if maybe I'm just forgetting like the crucial reason why that's not true. But yeah, so let's see. That down here. We got to get rid of this asset memory side. It's not necessary anymore. Release asset memory is here. There we go. So let's see. It's not really a good test because with anything that involves multi-threading, just running it and if it works is doesn't really tell you much. Because you could easily have like race conditions that just don't happen hardly ever, So yeah, but it doesn't immediately fail, which is something. It lets you know that you're not completely wrong. It just doesn't let you know that you're right. But the reason that that's interesting is because I like that aspect, because what that means is that really we can just do evict assets as necessary as something that is part of our allocation process. Right? And that's kind of nice. I like that. All right. So let's see what goes on here. Let's see what we need to do for our asset memory stuff here, since I don't actually know. Right? So let's see. We've got add asset header to list, and our load bitmap and all these other good things. So when we're doing this stuff, when we call acquire asset memory, if I wanted to change this, acquire asset memory, if I wanted to change acquire asset memory to allocate out of our own memory instead of calling the operating system, here is the part where I need to start to figure out how I am going to do that. And so we kind of had before, we had our arena, we had like a sub-arena set up for this, right? In here we said, sub-arena, right? And I think what I want to do there, right, is I want to kind of change that around so that instead of an arena, which is not really what I want anymore because this is not going to be like a stack like we were using, what I want instead is just to get that chunk of memory, right? So I want to get rid of this arena here and remove anywhere that was using it, which I think is literally just the allocation here, right? But what I can do now is I can go ahead and take some of that memory. So if I were to do something like, struct asset memory block or something, I don't know yet. Again, I'm not really doing anything serious here. I'm just going to sort of throw one of these in here. So we have like an asset memory block, and we'll just, I don't know, call that first block or something. And in here, we just have a total size, right? And then we'd have like a used size. So if I was just going to duplicate essentially the memory arena stuff first, then we could kind of start working from there. All right. So if I were to do that, then what I want to do is when I get my assets here, I'm going to make a first block thing. I'm just going to go ahead and get the. I guess what I'd want to do is get the entire size of memory that I want, right? Which is going to be this size parameter here, the thing they pass in. I'm just going to grab that. So I'm going to do like a push size onto the game asset arena thing. I'm going to get that back. And I'm going to say that I've got one of these asset blocks at the top of it for now, right? Asset memory block. There we go. Do a push size on that. So now we've got that. And then I'm going to go ahead and say that the first block total size, right, equals that size. And the first block use size is going to equal the size minus the part that I've actually used for storing that header, right? So I'm just assembling one of these little blocks in there, right? That's what I'm doing. Total size equals size. Oops, that's a pointer. There we go. And yeah, I don't actually need that to be a memory index because we're not going to let it get that big, but we'll just do this for now. All right. So if I do that, now I've got this block, and I'm just going to go ahead and sort of duplicate basically what we do in the arena just as a start for acquire asset memory, right? So as a start, what I'm going to do is I'm going to say, okay, we had this thing that does platform allocate memory. We're going to go ahead and pretend that doesn't exist anymore, right? That's not a thing. So off it goes. And I'm going to do the same thing with that release asset memory. I'm going to say, okay, we don't have that anymore. And so what I'm going to do, I could comment these two. Note, say this is the platform memory path, right? And then what I'm going to do is excuse me, I'm just going to probably also put that right there. Okay. I'm just going to go ahead and oh, no, I can't. I'm just going to go ahead and implement the simplest possible thing here, right? So for starters, I need to get a void pointer, which is going to come from like that first block, right? So I'm going to say I have an asset memory block or whatever it is. I'm going to get that block out of the assets. And then I am going to just grab the memory, right? So I know that the block right after the block is where the memory starts, right? Because I just put the block at the top of the memory. And I know that the block itself records how much is used. Oh, so I guess now that I think about it, I actually kept used size in there. That may not be a good idea. That may not be a good idea. You know what? I take that back. Total size. I'm going to do it this way. I'm going to say that the total size is actually this, and the used size is 0. In fact, that was the wrong computation for used size anyway. That was just a typo. So the total size, I'm going to say, is actually however much we allocated minus the asset block size, and then we haven't used any of it yet. Okay. Rather than saying, I could have initialized use size to be the size of the header. All right. So yeah, so that's where the result would be, and then block use size, right, would increment by whatever the size is that we were trying to acquire. And so I'm going to assert here that the used size is going to be less than the total size. And in theory, that assert should fire because we will run out of asset space and we're not able to free anything yet, right? So yeah. Let's take a look. Plus equals size. There we go. And let's take a quick look here, right? There we go. So eventually we just run out of space, and that is the end of it, right? That is the end of our little party. We hit the assertion that says, if I were to actually, you know, this thing is that big, right? This is how many bytes it's got in it. This is how many bytes we're using. So we've got this much left, right, before we hit the end of the block. Oh. Wait, what? Total size minus block used size. How is the used size? Oh, pfft. We actually went over there. That's no good. I want block used size plus size, right? That's what we actually want. Let's try that one more time. There we go. That's more like it. So this is how much we have left, but the size of this particular asset is this, so it won't fit, right? And so what I want to do here is I want to then try to, this is the point when I actually detect this, right? What we want to do is now, instead of that being an assertion, what I want to do is say, if what I would have done, like the block size plus the size, if that would overflow, like if I can't find a place for it, then I am going to, and in fact I'll put it in here as an assert after the fact. Right? If I would have overflowed, then that is the time when I actually would start to evict things, right? So it's almost, it's really just a thing that's gonna, right? We want to see when we hit our memory limit, and when we find that we literally can't put anything else in there, that is the time to then go start reclaiming stuff, right? I hope that makes sense. Okay. All right, so that's what we want to do, okay? Unfortunately, we don't have any ability to actually free stuff yet, right? We have no way of doing anything like that. Because when we do a free on something, we don't even know like what block it's in, right? Like we have no idea. So we need to start figuring out some way of keeping track of this stuff. So again, I'm going to do something that's, I'm going to do something not particularly intelligent, right? I don't claim that this is at all good. I'm just going to sort of start to work my way through the problem of getting this memory into some sort of a flexible shape that will allow us to fulfill the requirements. And they may not be great. The performance might not be great of it or whatever, but I'm just going to try to sort of work through it to figure out what I want to do here. So what I'm going to do is I'm going to introduce an asset memory block sort of, I don't want to call it a tag because that means something in our asset system already. So it's sort of an asset memory block, almost, it's like a little thing that gets inserted, like a waypoint, or what do I want to call this? It's sort of like a partition. I don't know what I want to call that. Asset memory block, barrier, stripe, marker. How about marker? Right? So these block markers, what I want to do is every time I allocate something, I want to insert one of these block markers so that the block marker will tell me what it is that I need to do with this thing. And you know, I could actually just use asset memory block for that, potentially. In fact, that may be the easier thing to do instead of having to do a separate thing. So let's say I've got this, right? It's got the total size, use size. I'm going to change sort of the way that it's conceptualized. I'm just going to say that my asset memory block, right, oops, just has a size. That's all it has, right? So I know how big this asset memory block is, but it also has sort of a notion of where it is relative to other things, right? So there's also an asset memory block, like that's the previous block from this block, right? And maybe there's a next. So they're like, let's say these things are threaded through here, and there's a size, and then there's like whether or not this block is used, right? So there's like something like this, right? So I'd say asset memory block flags, asset memory used, right? So instead of having that sort of stack-based thing, I'm just going to make like this little kind of lame little guy, right, who just kind of sits there and says what's going on with this thing, okay? So if I were to do that, how would this now look? Well, at the outset now, asset memory block, when we create it, it's going to be different. It's going to be a little bit different, right? So what's going to happen here is we're going to push size on this. Previous is going to be equal to nothing, right? Next is going to be equal to nothing. I don't know if we want to doubly link that guy. Probably not, is my guess. You know, I don't know. That's a good question. Maybe we do want it to be circular. Maybe we do want it to be circular. I don't know. I don't know. Let's just do it. Why not? I'm curious. So there's our memory sentinel, right? We've got an asset memory block here. And we're gonna go for it. We're gonna just go for it. You know what? Fortune favors the brave, people. Okay? That's just how that goes. So I'm going to say that we've got this memory sentinel here, right? And it's got a flags of 0. And it's got a size of 0, because it can't store nothing, right? And it's got a previous pointer that points to itself. And it's got a next pointer that points to itself, right? And then what I'll do is I'll say that I want to insert a block into this list. So what I want to do is say insert block, and I want to insert it after the memory sentinel. That's what I want to do. And this is the memory for that block, right? And this is the block size, right? Something like that. And then the insert block call is just going to be in charge of like sticking some memory in to this thing, right? So there's the memory, and this is the asset memory block that it comes before. So this is the previous block, right? Does that make sense? So how do we do that? Well, we've already seen how to do that. It's really, really basic, right? Like I said, we just say that the block itself, the sort of control feature for the block, has to go into the specific location itself. Excuse me. There's some reasons why, you know, I feel like I kind of want this to be aligned as well, which it wouldn't quite be at the moment. So, you know, we might do something more like this. Just throwing that out there. So yeah, just because we want this thing to be on a 128-bit boundary, but that's kind of separate. We'll get to that stuff a little later on down the party line. Anyway, so when we're doing this, what we want to do here is, and I guess we could call that a memory index, but or U64. So what we want to do here is we want to stick the block into the memory thing. We want to probably also assert that the size is greater than the size of one of these things, because we're never allowed to actually make one smaller than that, or we can't fit the control block in it, right? We would then say that the block's size is whatever the size is minus the part we just used, just like we did before. And then we would go ahead and link it up. Again, just the standard linked list thing here. Where we say like, okay, our previous is our previous, and our whatever was after our previous is our next, right? And then we just do the standard thing here, where our previous next is now us, and our next previous is also us, right? So we just kind of insert our link into the rolling link there, right? Okay. So now we have our memory blocks. We know that the flags field, I guess, well, we didn't actually set that. So we know that the size field, but we didn't set the flags. The flags field should be 0 because it's not used. So that's just how we would insert that block, and we would probably return it in case the person who was adding it, asking us to add it, wanted to do something with it, right? So yeah, that's all fine. Nothing particularly fancy there. And so in here, I'm just going to put that up at the top so we can do that block insertion stuff. So now we will have inserted a block. And so now if we wanted to allocate memory, and again, this is going to be some of the worst code ever for the moment. We do acquire asset memory. We just need to look first to see, is there a memory block that could actually hold what we want to hold, right? So we're literally just going to do that like this. We're going to say asset memory block. Instead of first block, we're going to say find block for size, and we're going to pass the size. That's going to return us a memory block. If we got a block back, we will assume that that block is able to hold us, right? So we'll do an assertion and say that the use size plus size, right? We'll do that thing, assume that it can fit in there, right? And then we'll just go ahead and make that all that same stuff that we were doing before. Block use size plus equal size, blah, 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 right? All that stuff should just work, right? Oh, wait, no, sorry, but except for this part. So what we need to do now, since this block is going to be used, is we need to split the block, right? We need to split the block in half. We need to use one part of it and reserve the other part of it. So I'm going to basically say something goes here, not that. And then what we have to do is finish the rest of this loop. So we want this thing to go until it actually is able to place it. So if we do find block for size and we are unable to find a block, right? Then what we want to do is we want to evict an asset, right? We want to evict whatever the asset is that we could have evicted. We want to be able to do essentially this path, right? So while we're in this loop, we want to say, okay, find a block. If we found a block to put it in that block. If we did not find a block to put it in, right? And by the way, we're done at that point, right? We don't have to keep looking. If we did not find a block to put it in, then we have to start evicting assets, right? So then we would do something where we go like, okay, we would go ahead and say, take the asset memory header, the least recently used one. We would assume that there's something to free, so we start trying to free it. We come in here, right, get that asset, we free the asset. We would want to do this until we actually freed an asset, right? So this one would also want to do something where it would say, okay, start with the previous, go until you hit the sentinel, and always do header, always walk the list kind of backwards, right? As soon as you find one that you can evict it, and you are done, right? Another thing I guess we could do is right here just see if the block that we were evicting the asset from, we kind of know that that's the block we want. So really, I guess it looks like this, something like this. First, we try to find a block for the size. From then on, we just use whatever block this asset was actually in, and we want evict asset to return us whatever that block actually was, right? And so here's evict asset, right? When it goes to release asset memory, we would want that release asset memory call to tell us what the actual block was that it released, so that we can check that resulting block to see whether or not we could put the asset in there, right? Does that make some sense? It's kind of an optimization, right? So I could do something like this for now. right? I could do something like this for now. To do, actually do this instead of just saying you're going to do it. Right? And so what do these things look like? Right? What do these things look like? Well, find block for size, again, if we just don't think about performance or anything else, we're just trying to make it work, it's not too, and this is probably not an inline anymore, it's probably not too tricky, right? Find block for size, all it does is scan through all the blocks, and if there is a block that is not, if it finds a block that could have space in it, that's, you know, if it finds a block that's not used that could fit it, it could return it, right? It could literally be that simple, right? We could also find the one that was the best match block if we wanted to, right? For now, we're not going to do it, so I'm just going to put to do, right, best match block. And in here, I'm just going to loop through all the stuff. So we've got asset memory block equals sentinel next, right? So that's asset memory sentinel, right? I'm going to say that I loop through while the block is not equal to the memory sentinel. And we just kind of walk that chain, like so. Yeah? And so when I look at a block, I say if the block flags is not used, right? So if whatever it is used, that would come back true. So we do like that. If the block flags is not used, then we say if the block size is greater than or equal to the size we want, right? Then we can use it. Now, there's a caveat here, which is that actually the size that we need it to be, because we're going to use up the block, oh wait, no, I take it back. There is no caveat. It's fine, I think. We'll find out. Okay, so we're going to come through here, and what we want to do is say, here's our result. This is the block. We would say the result equals this block, and we are done. And we return the block back. So this just scans through everything, tries to find a block that we could put it in. As soon as we find one, again, we're not doing a best match. We just, there it is. We just give it back, right? Happy days. Everyone's happy. We're done, right? And so that would find it. And then the question is, what do we do when we actually find it, right? Well, what we do when we find it is we have to take that block and either split the block in half or just use the block. So if the amount of space that was left over was going to be appreciable, we would split the block. If it wasn't, then we wouldn't, right? So here we go. We take the block, we do find block for size, right? If we found the block, we say, let's assert that however much the block size is less than the size that we need. I'm sorry, other way around. Assert that the size that we need will fit in this block, right? And I just want to double check. When I did insert block, we do set the size properly to be, to be what it, okay. So we figure that out. We then go ahead and get the memory for the block. So we say, okay, the result here is going to be just right after the block. That's what the memory we're actually using is. But because we're only using a certain amount of it, we may then want to split the block in half, right? And if we were to split the block in half, well, I guess there's a couple things we want to do here. So first of all, we want to set the block flags, right? We want to set the fact, we want to record the fact that we use this block, right? So the block flags are now going to be set to used. And the other thing we want to do is we want to set, we want to see if the block size, if the remaining size, basically, right? So the memory index remaining size. If the remaining size is going to be anything appreciable that we could actually use, so whatever we'd say, if remaining size is greater than, I don't know, let's say if the remaining size is greater than threshold, block split threshold, right? And that's some kind of a thing that's just like, you know what, it's gotta be at least 4096. It's gotta be at least a page. I'm making this up. It's probably something bigger than that, right? But let's say we do that, right? So if it's at least that, we split it, right? So if the remaining size is within the block split threshold, then what I do is I do an insert block in the remaining section, right? So what I do there is I say, okay, the block size is now actually going to be the block size minus whatever the part is that we're going to use there, right? So yeah, whatever the block size was before, we're shrinking that down, and we're going to actually use this bit, right? That's correct, right? Block size minus size is the remaining size. Yeah. The block size, we subtract that, and then we say, okay, let's put the actual block, a new block header in. It's going to be inserted after us, right? It's going to be whatever the remaining size was, and its location. Its location is going to be wherever our result was plus the size that we used, right? Like so. And that'll automatically link it up, and off we go, right? So yeah, pretty straightforward, not particularly difficult. We now have the result, although the void star needs to be out here, or we won't be able to return it. So that's how that actually worked. But that seems about right to me. Yeah. So that's all good. And so then the only thing that we would need to do to follow that would be in release asset memory. We would then need to be smart about that as well. So we need to recover the block, right? So we need to do the asset memory block. Block is going to have to be equal to, the memory minus 1, right? We need to kind of back it up 1. So that gets us our block back. And then we can just go ahead and say, oh, the block, the flags are equal to, and equals not. So we can clear that asset memory used. We can clear it out to say it's not being used anymore. And then the only thing we really need to do at that point is take a look at our previous and nexts and merge them, right? But I'm not going to do that now because we're running out of time, right? I only got about 3 minutes left. So we'll just do merge. Now, that's one of those things that, like, I've just typed a ton of code in. There's no way that's going to work, so this is just going to be a crash festival. We'll debug it tomorrow. How is it that every time I say it's going to be a crash, it doesn't crash? How is that? Okay, that's more what I was expecting to see. But it still didn't crash. All right. At least I can say it's a bug festival. So we have a ton of work to do there, obviously, that we need to figure out and make sure everything is more copacetic than that. So we gotta take care of all that, and we will take care of all of that. But for now, I'm going to go to the Q&A and take questions. So if you have questions about what we just did, please ask them now. Put Q: in front of your question, and I will be able to see it. There we go. Oops. Questions and answers. Questions and answers. I'm feeling good about this. As stupid as this algorithm is, I feel like it's more fun to write this yourself so you guys can kind of see how you write a general purpose allocator, even a really lame one. I think is more fun than just having the operating system do it. So I think we're going to go this. I think I'm going to pull out the operating system one and we're going to do it this way. James Woodman, given that this is an optimization problem, it seems like we'll want to have a system for profiling asset use and eviction and check its output periodically as the game and assets grow over the next year or so. Should this be on the agenda in the near term? So actually, it is on the agenda in the near term already. You will notice that I put this next. And that is because now I feel like we have sufficiently complicated stuff in the game already in the engine that now is the time to be able to see that stuff. Because, yeah, we want to be able to know stuff like how many assets are evicted or allocated per frame. We want to know stuff like how many memory blocks there are and how fragmented they are. Like, we'd like to see that stuff. We've got threads. We'd like to see what the threads are doing. So there's pretty much no question that we want that. And so we've gotten things up and running. You could make a game with what we have now, right? We've got renderer, we've got asset system, we've got like good stuff in there. We've even got sound playback already, right? So I think now is the time to kind of go, all right, let's put some debug code in there so we can actually visualize everything and kind of tighten things down. And because some of these other things like doing lighting or whatever is kind of just it's just a visual quality improvement, but it doesn't actually, like, we could ship this game without ever doing this to do, right? We just wouldn't have to have, we'd just have boring lighting or something, right? But this is definitely something that we wouldn't really be able to ship the game without and have a high quality, because we need to be able to see this stuff. I'm not clear on what happens in the else when we fail to find a block. Could you go over it? Sure. Well, first of all, keep in mind, we've got bugs. So what happens in the else is probably wrong. But yes. So here's how this loop is starting to take shape. We know that we need asset memory. We start out by saying, okay, try to find a block in our linked list of memory blocks that the asset could just go into, right? If we find one, then this is the part that just splits the block in half and stores the asset in the first half, right? And if it can't split it, then it just doesn't bother, right? Otherwise, if that means that we're out of memory, essentially, meaning we have filled all of the memory that we have to fill, possibly including fragmentation. So it doesn't mean we've perfectly filled it, but we've mostly filled it, right? We then loop through all of the assets in reverse order of recently used, right? So the first asset we will look at is the one that we touched the furthest in the past. Because our assumption is that the thing that we used the longest amount ago is the one that's least likely to be necessary on like the next frame, right? So we come in here and say, okay, what's that asset? If that asset has a valid load flag set, so it's like we've looked and seen that it actually is loaded, and not like in the middle of being processed by a background task or something, right? Then what we do is we just evict it. Goodbye, it's gone, right? And when we evict it, that frees up some memory. So that allows us to then ask again for a block. We go back through the loop and see if we can find one now. Now the reason I put it to do here was because there's no reason for us to keep looking through blocks again once we free this. Because when we free this, we then know that we know that there were no blocks that could hold us before. So when we free some memory, we know that the only block that could possibly hold us now is whatever the block was that was created by that free. And so that's why I say like we want to go ahead and do that shortly, right? Why do we need to check the remaining size versus the threshold? Why not just use the remaining size if it satisfies the request size? So these are two different things. So when we do find block for size, we assume that the block it returns, if it returned a block, can fit the size. So we always place the asset there if one comes back, right? This is the code that places the asset there, right? We mark the memory block as used, and we place the asset there, okay? So this check is only to see whether the amount of memory left over in the block warrants creating a new free block in that location to be used later. Because I don't want to bother, if there wasn't enough room to ever store an asset in that block, we should not bother, right? In fact, I could do a thing here where it was like to do set this based on the smallest asset size, right? And so it's basically just saying don't bother creating a block that we're going to like think about in the future if nothing could fit here. If we know that if we know that our smallest asset is 16K big, then we never need to create a block that's smaller than 16K because nothing could ever go there, right? So yeah. But that's not really, so okay, that's not really true. There is a separate thing that could happen. If the block after this block got freed and wanted to take some of the memory from the preceding block, right? That could happen. So what we could start doing, you know, I could put a to-do here and be like, to-do, actually record the unused portion of the memory, right, in a block so that we can do the merge on blocks when neighbors are freed, right? So we could do that as well. Snafuzel, how come this memory management system is strictly limited to game assets and not other things as well? Well, the reason for that at the moment is just because we don't have anything else that needs it. In the future, if we find that we have some other part of the code that wants to do general purpose allocation for some reason, we could pull this out and use it there. But that would be the time to do it, right? Not now prematurely. What will the GUI handle? What GUI? Grumpy Giant 256, if this were a commercial product, would it make sense to use malloc instead here, or write your own anyway for managing assets? Well, I guess what I would say is if this were a commercial product, I might have gone ahead and said, I actually want to do all the necessary work to do like asset tiling and making sure that I actually never have to do general purpose allocation. I might have. I don't know that I would have, but I might have. Most of the time, I try to make sure everything that I ship goes through just fixed block allocation. So I really don't know, is the answer. I don't know. I certainly never call malloc, but you know, if you really have a general purpose allocation thing to do, then you know that is roughly what you're using. So that's fine, right? So yeah, I mean, I think if you actually determined that you really needed a general purpose allocator, and it wasn't just like, for example, what we're doing it now, where it's just kind of like, yeah, it would be interesting to do one, so let's do one. If you really determined that's what you needed, then I would say, yeah, I don't know that I would necessarily use malloc. I might go try to find a public domain or open source allocator that I felt comfortable using, and integrate that into the code base so that I knew that it would be the same on all the platforms and not differ based on the C runtime library that I happen to be using. Because I don't love that. I don't love not knowing what my malloc is doing. And if I use the C runtime libraries, that means every platform will do it differently. And that doesn't thrill me. So yeah, I don't know if using malloc would be the right call, but writing your own allocator isn't necessary. You could use one that existed. Much like in Handmade Hero, in general, we write everything from scratch because that's the point of the project. That doesn't mean that if you found a open source one or something that you trusted, that you couldn't use it, right? Like I've said before, you know, I like sometimes to use like Sean Barrett's libraries, right? They're good. And so it doesn't bother me to use that like it might bother me to call malloc, which I don't necessarily trust because I don't have a whole lot of confidence in the people who wrote it necessarily. Any possibility of using Markov chains? Probably not. It's looking like Vulcan, if it gets released in a timely manner, is going to be a good choice for hardware rendering. I just read that you have control over all memory to avoid any unknown allocations. Explicit memory management in Vulcan allows applications to use custom allocation strategies, for example, to allocate all memory upfront and avoid any allocations during rendering. So, two things about that. One, I am on the Vulcan advisory board, so I cannot really comment on Vulcan things due to NDA. Second, I would say that that statement may be a little misleading. But I can't really say much else about it without being NDA-ish. I would be interested to know where you read that and who was saying that, because I don't even know who was actually allowed to say something like that. Yeah, I guess I can't really say much about that other than I find that statement to be highly misleading, although it could technically be considered true, depending on how you wish to define some of those words. And I can't elaborate and I'm not sure why whoever said that was allowed to say that in the first place. Have you thought about having a prefab asset that people could use to make more complex assets, like a whole house with functional doors? I don't know what that means. The GUI mentioned in the to-do list. The GUI mentioned in the to-do list, you're talking about this. That's just so that we could, like, when we get all this debug stuff in there, you're going to need to be able to, like, view stuff that wouldn't all fit on the screen, or you wouldn't be able to see the game if you stuck it all on there. So we kind of need a little GUI for, like, being able to pick what am I viewing in the debug view right now. You know what I'm saying? You keep saying split the block in half. What do you mean? So what I mean by split the block in half, I don't know where my pen is. There it is. What I mean by split the block in half is that here's what I'm looking at right now, right? We've got a little bit here where we've got, you know, a previous pointer and a next pointer, right? Then we have flags and we have size or whatever, right? So we've got this little header up here, and then we've got some memory, right? So this is just a chunk of memory that we can use for stuff. We come through, and in this part of the code here, we say find a block. We get back a block. So what we're talking about is a pointer to this thing, right? So we say, okay, great, we found a block. We'll place the asset right here, right? And then we have to see how big it is. So maybe the asset takes up this much space, which means that this is a pretty usable chunk of memory, right? So when I say split the block in half, what I mean is I now need to make a marker that says that this is available. So what I do is I make a new header and I stick it in here. Its previous pointer points up to this guy. This guy's next pointer now points to here, and this next pointer points to whatever this guy was pointing at. So I've inserted this block into the chain. I've split this block in half and inserted this secondary block into it. And then whatever's remaining is now available for use again. Because this is used, but this is free. That's what I mean by split the block. Mojo Bojo, this is where I read it from, and there you've pasted the link. Copy link address. I will see if I can load up that link that you have pasted. It looks like it is a link from Image Tech blog. Let's see. Ashley Smith. I do not know who that is. Vulcan is a next-generation high-performance graphics and compute API developed by the Kronos Group. Okay. Here is a summary of Vulcan extracted from the official press release. Let's see where this is. Allocation. When you call GL Text Storage 2D in OpenGL, the driver has to allocate memory for a two-dimensional or one-dimensional array texture. The function and the memory allocation process represent a black box. In Vulcan, however, the memory allocation is done by the application. This means that the application knows more about what type of memory it is using and, more importantly, how much memory it is using, which should be more useful for applications that are memory-bound. This is in contrast to using out of memory. Explicit memory management in Vulcan allows it. So I don't know what I'm allowed to say and what I'm not allowed to say. All I would say is I would give this blog absolutely zero. I would ignore absolutely everything you see in that blog. That's all I have to say about that. Will the debug GUI have a cool console like Quake or Unreal? No. I don't think that would be a good use of my stream time. All right, looks like that's the end of questions. I see no more. All right, so I will wrap it up. Do a little wrappy poo. Let's see here. I'm kind of excited about this little memory thing. Even if it's lousy, I'm the kind of person who actually prefers code that I completely know how it works to code that may be better but that I don't know. Because it just allows me to think through everything in a way that I can't otherwise. I don't know. So I'm kind of excited about this. We'll have our own little memory guy. And maybe we'll at some point try to make him even kind of good. At first it won't matter. It may never even matter really. Because computers are very fast and this is not something that happens that often. You know, it's something that happens a few times a frame, and at that point, you have a lot of leeway, right? It's not like pixels where there's millions of them being filled. So who knows? But anyway, it's kind of cool. I'm kind of happy we decided to do it, or when I say we, I mean me. But you know, I mean, it's a royal we. Anyway, let's go ahead and close it down here. Close it down. Thank you everyone for joining me for another episode of Handmade Hero. It has been a pleasure coding with you as always. If you would like to follow along with source code at home, if you pre-order the game, it comes with the source code. So that's something you might want to check out. You can go to handmadehero.org. You can do it with the little pre-order button. That's all it takes. And you can play around with the source code. I update it every night after we finish coding here. We also have, hopefully this weekend, I can get maybe the GitHub access stuff working. I'm looking forward to that. Only because I know people like that. And I have been doing the work of keeping the GitHub up to date. And I think it's working. You know how Git is, but I think it's working. So hopefully that will also happen a little further down the line. We also have a Patreon page. If you want to just support the video series, you can subscribe to that. And we have a forum site where if you want to ask questions or take a look at an annotated episode guide, there's just good resources on there for people trying to learn from the series. There's also a tweet bot that tweets the schedule. So if you want to catch this stream live, that always lets you know when it's going to be live. I broadcast the schedule on the weekends, and then every day kind of gives a little reminder tweet to let you know when it will be for that day so that you can plan to see it if you would like to. So that's about it. I hope everyone has enjoyed our brief little foray into general purpose allocation, which we will continue tomorrow, 5 p.m. Pacific Daylight Time, right here on Twitch. And we'll try to get everything kind of buttoned up a little bit for our basic general purpose allocator. We should be able to have it working fairly nicely tomorrow, I think. It just might not be very efficient at finding memory blocks. But hey, that's okay. Things can get more efficient later. So that's it, everyone. Thank you for joining me. I hope you have fun coding until I see you tomorrow. Until then, take it easy, everyone.